For this example, we'd like to use spherical coordinates to solve a volume equation about an intersection. So what we want to do is we want to find the volume of this ice cream cone. So what we're trying to do is we're saying, I've got some sort of cone here, and on top of it's the sphere. So I want to intersect the sphere. I'm going to take everything on top of the sphere and everything below the cone or inside the cone. And so if I were to take the sphere and smash it on top of the cone, or everything that wouldn't fit in the cone just falls off, I want to find the volume inside the cone and the little rounded spherical piece on top. So just a very simple basic idea. And what I've got is a sphere that's rho less than or equal to 1. So what that tells me is that the distance from each point on this each point is less than or equal to 1. So that's a standard unit sphere, or a sphere of radius 1, and everything inside. So it's a solid sphere. And this cone, I guess technically that should probably be less than or equal to, but it's not really a big deal, is this z equals x squared plus y, or square root of x squared plus y squared. So what we have to do is we have to figure out what the spherical coordinate representation of this is, and then we have to set up an integral to solve this particular problem. So the first thing we got to do is we got to say, all right, what's a spherical coordinate representation of that equation? So to do that, we go back and we reference the fact that z is rho cosine phi, x is rho sine phi cosine theta, and y is rho sine phi sine theta. Okay? So then what we've got is rho cosine theta equals the square root of rho squared sine squared theta, or phi cosine squared theta, plus rho squared sine squared phi sine squared theta. All right, so let's factor out what they have in common. We can say rho squared sine squared phi cosine squared theta plus sine squared theta. So we know that's the Pythagorean identity. That's just 1. So we're going to say square root of rho squared sine squared theta. Now we normally have to be careful with this. It'd be the absolute value of sine phi, but in this particular case we have a little bit of a understanding. If you look at this, you can clearly tell that the phi is going to be less than pi over 2, some value less than pi over 2. So as long as you keep track of that, it's not so big of a deal. So we have rho cosine phi is rho sine phi. The rho, if we divide both sides here, or divide both sides by rho cosine phi, we get sine phi cosine phi tangent. Well, phi, in that case, phi is pi over 4. So what we actually have is, instead of this equation, we just have this equation. We know that phi is pi over 4. Now, does that make sense? Well, let's think about it. If I'm thinking about a cone, if I don't make any restrictions on theta, it will always rotate all the way around. Think about anytime you don't have a variable in the equation, it always covers all the possible values. So that means it rotates all the way around like a cone. And there's no restriction on rho, so it goes infinite. So that makes sense because a cone goes infinitely high, and all the eventually the distances go off to infinity. In this case, it doesn't because it's bounded by the sphere, but in general, it does that. So the only real defining characteristic of a cone is how bent it is, right? If phi was like pi over 100 or something, very pretty small, you have actually if pi over 100 doesn't come very far off at all and it shoots straight up. If it's very close to pi over 2, it's very flat. But no matter what, if I take this and I kick it over a little bit and then I spin it all the way around, I have a cone. Right? If I fix phi and I spin theta, I get a cone, and then of course rho goes off to infinity. Anyway, so that's pretty simple. That tells me that for this particular ice cream cone, I know that phi will start at 0 and fall no further than pi over 4. So that tells me that it falls no further than pi over 4. Now what I notice here is that it also rotates around completely. So that tells me theta goes from 0 to 2 pi. Now what about rho? Right? Rho should be going, it's on the sphere, rho's less than or equal to 1. But when it hits this point, when it hits that intersection point, what you actually find is that since it intersects the sphere and then just goes all the way down, this is still a radius. So this still has length 1. That still has length 1. So if we're covering the inside of the cone, rho in this case, still only 0 to 1. It's pretty simple. So we set that up, and don't forget, we always have a rho squared sine of phi d rho d phi d theta. So then we solve. Okay, well, for this, we say that's 0 to 2 pi, 0 to pi over 4, 1/3 rho cubed from 0 to 1 d phi d theta. Well, when 0 is plugged in, that vanishes. When 1's plugged in, it just becomes 1. So we have 1/3 d phi d theta. So that becomes 1/3 phi from 0 to pi over 4 d theta. Well, when 0 is plugged in, it vanishes. When pi over 4 is plugged in, that becomes pi over 12, pi over 12 d theta, which becomes pi over 12 theta from 0 to 2 pi. And in this particular case, again, theta vanishes when it's 0. This term vanishes when theta is 0. So we plug in 2 pi and we get pi squared over 6. So that's pretty much how you solve this. Let's do just a hair of reasonableness testing. Remember that the area of the sphere, or the volume of the sphere, 4/3 pi r cubed. So in the case that the sphere is radius 1, we should have 4/3 pi. Now in the case of the volume of the cone, that's pi r squared h. In this case, what you actually find is that r and h are the same, because if you go all the way back to here, well, that's actually x squared plus y squared is r squared, right? And so that's actually r. So this is the sphere where the height, so that if you take the height and you take the radius to the point, you actually have the same sphere, or the same cone. So in this case, it's actually pi r, or r cubed, or h cubed, you might say. We have to be a little careful because in this case, h isn't 1. All right, that's 1. So since these two things are the same, it's a 45, 45, 90 triangle. So each of those is 1 over square root of 2. So we have pi over 2 square root of 2 as our volume there. All right, so the reason why I'm saying that is because you should expect this number to be bigger than this, but less than that. All right, so this is clearly bigger than this. This, I mean, for very, very broad round numbers, call pi 3, right? So 9 over 6 is roughly 3/2. I mean, very roughly 3/2. It's actually larger than 3/2. But this is like, if pi was 3 here, this is not only 3 divided by 2, it's divided by another square root of 2, so it's clearly less than 3/2. So since this is larger than square root of 3 over 2, and this is less than 3/2, okay. Now 4/3 pi, again, this is larger than 3, so this is larger than 4, which is going to be larger than pi squared over 6. So we can be reasonably certain that these just tell us that we've done something, we're in the ballpark. We maybe not be perfect. This is the right answer, but we just have to be careful about how we approach these and try to see if we can understand if we've done it correctly.